Well, having learned about molality, we are ready to wrap up our final set of topics in Chapter 9. And as the title says, we're going to be considering freezing point depression and boiling point elevation. So what is that? So if you've ever wondered why they put, we know why. We know they put salt, why they put salt on the roads or rocks and things like that. Whenever it's supposed to freeze, we understand that it's supposed to help keep the roads from freezing, but maybe you've never investigated it to see exactly why that is. And the reason that works is it's because of this idea of freezing point depression. I'm pointing at my computer like you can see it and you can't. So sorry about that. But anyway, freezing point depression is why the roads don't freeze unless it would have to get super cold compared to what it normally would be for freezing. And so the idea is that when you have a liquid, if you mix anything with that, if you create a solution with that liquid, the effect is going to be that it's going to lower the freezing point for that liquid. And that works for water. So by mixing in the salt, by putting the salt out on the road, whenever the rain falls or the snow falls and that salt begins to mix in with that water, it lowers its freezing point, and so it stays liquid and doesn't freeze over. And so what we're going to learn in this chapter is how much will it lower the freezing point. And of course, that's going to depend on the concentration of the salt, how much salt you've added to the water, okay? And so we have a formula for that, and that formula is change in T. Hopefully you've seen this before. Use this Greek letter delta. That's an uppercase delta there, which means change in something. The capital T representing temperature. Change in T equals negative I times Kf times M. Little m for molality. So this is for the freezing point depression, all right? And we know it's freezing point for two reasons. This negative sign right here, because with freezing point, we're lowering the freezing point. So it's going to be that the change in the temperature is going to be negative. And then also the reason we know this is the formula for the freezing point depression is because of this lowercase f here. So Kf is what we call the freezing point depression constant. All right, and it is a constant value. In other words, it's a number that doesn't change for each liquid. So each liquid has its own freezing point depression constant. All right. Most of the problems that we're going to be using are going to involve water. And so for water, that value is 1.86 degrees Celsius per molality, lowercase m. And so we'll just use that value. If we know that the liquid that we've added the solute to is water, then we can use this freezing point depression constant. I'll give you that in the problem if you need it. So M, like we said, this is molality. And this is temperature, so change in temperature. And then what's this value I here? I is the number of ions, okay? So what do we mean by that? Well, think about salt, for example. If I have salt, which has this chemical formula, there is a single Na plus ion and a single Cl negative ion, right? A single sodium ion and a single chloride ion. That makes a total of 2 ions. And so if we were mixing salt in with water, this value I would be 2, okay? But if you had a different ionic compound, like the example that we're going to do in the book has MgNO3, and so magnesium nitrate, right? And I drew that 3 kind of far out, don't like that. Magnesium nitrate. For this one here, we have 2 Mg, not 2, sorry, we have a single Mg2 plus ion, and then, but we have 2 NO3. NO3 has a charge of 1 negative. We have 2 NO3 ions because of this 2 right here. So the total number of ions, 1 Mg, 2 NO3s, is going to be 3. So I equals 3 if that's the substance that we're mixing in with the water. All right. So not a hard concept, just something that you need to understand. Now, we don't always mix in ionic compounds with the water. Like I said, anything that you add to the water is going to lower the freezing point of that water. So what if we added sugar, for example? Sugar is a covalent compound. It's not an ionic compound. And so if it happens to be a covalent compound in the problem, use I equals 1 for that because it's a single sugar molecule. It doesn't split up into the ions the way that the ionic compound does. So just think of it as I equals 1 in that case. All right. Well, let's do a problem and actually use the freezing point depression. And so let me see if I can erase this stuff here without removing everything, just so we can keep our formula on the board here. Well, it was going really well. Now it's not going to work for me. Oh, wait a minute. Let's see. Here we go. Delete that. Delete that. My delete key quit working. So there we go. Okay. So we're going to use this formula. And the problem, this is example 9.7 in the book. Example 9.7. The problem says a chemist dissolves 50 grams of MgNO3. 50 grams MgNO3. Or magnesium nitrate in 275 grams of water. So 50 grams of this, 275 grams of H2O. What is the freezing point of the solution? Okay, so there's going to be a new freezing point because we've added something to the water. And the original freezing point is going to be lowered, right? And so they tell us that Kf, like I said, this will always be given to you. You don't have to memorize any of these freezing point depression constants. Kf for the water is going to be 186 degrees, not 186, 1.86 degrees molality, okay? So we're going to use this formula here to figure out the change in the temperature. And then we're going to have to take the freezing point, normal freezing point of water, and subtract that value from it to get the new freezing point, which is what they're actually asking for. Okay, so we've got MgNO3 We know then that because of this, we know I is going to be equal to 3, right? We just looked at that because we've got 3 ions there. They've given us Kf. But in order to find change in T, the other thing we need to find is this little m, which stands for molality. Well, we just learned the formula for molality, right? Molality equals the number of moles of the solute divided by the kilograms of the solvent. And so how many moles of solute do we have? Well, we're going to have to calculate that because they gave us the solute, which is the magnesium nitrate. They gave us that in grams, not in moles, right? So let's do that quick calculation down here. We go to our periodic table, right, to see what the molar mass is of MgNO3, and when we plug in all of those numbers into our calculator, we come up with a molar mass of 148.33 grams per mole. So then, to convert from 50 grams of MgNO3 to moles, we multiply 50 grams times 1 mole divided by 148.33 grams, right? And that's going to give us 0.337 moles of MgNO3. I need to just keep saying magnesium nitrate. That's much easier to say. All right, so we've got our number of moles, right? We're going to put that on the top here, 0.337 moles. But we also need the kilograms of the liquid. And they don't give us the liquid in kilograms. They give it to us in grams, but we're pretty smart at this point, and we know you just take the decimal place and move it 3 places to the left, and that will give us 0.275 kilograms of water, right? So remember, this is the solute, the number of moles of the solute. This is the number of kilograms of the solvent. And so we punch that in our calculator, and we get a value of 1.23 lowercase m. That's our unit, right? And so now we're going to just plug all of that information in our formula here. That means that the change in T is going to be negative. We've got 3 ions, so negative 3 times the Kf, which is 1.86 degrees Celsius over molality, times 1.23, that's our molality. Our m's cancel out here, and so we're going to be left with a value that is degrees Celsius. And again, plugging that in our calculator, we get negative 6.86 degrees Celsius. All right. Now, again, what did they ask us for? They asked us for the new freezing point. What is the freezing point of the solution? And so we know that that means this is our this value here is the change in the temperature. So in other words, the freezing point got lowered by 6.86 degrees Celsius. So we're going to have to take the original freezing point of water when it's all by itself, and we need to know those values. You need to know the freezing point of water and the boiling point of water. And notice this is degrees Celsius, so you need to know that in Celsius. And so let's just make sure we know, we don't forget. This is something you should have memorized. The freezing point of water is 0 degrees Celsius. The boiling point of water is 100 degrees Celsius. So much easier in Celsius, right? Fahrenheit's 32 degrees and 212 degrees. But in Celsius, it's just a 0 and 100. So that means that the new freezing point, right? The new freezing point of our water is going to be the original freezing point, 0 degrees Celsius, minus 6.86 degrees Celsius to give us, it actually ends up being the same value, right? It ends up being the same value in this case only because the original freezing point was 0 degrees Celsius. If we were working with a different liquid that didn't have a freezing point of 0 degrees Celsius, we would have to do the math here. But for the water, it works out pretty nicely because it starts at 0, the value is the same. So that is the change in temperature turns out to be the new freezing point of the water, okay? Now, just like we saw that with freezing point, it will be lowered whenever you add a substance to the liquid. The reverse happens to the boiling point. If you add something to the liquid, you're going to elevate the boiling point of the water, which is why we have, why there are two topics in this lesson, right? We're looking at boiling point elevation and we're looking at freezing point depression. So let's do the same type of problem, but using the boiling point. And the formula is going to be a little different, right? Our formula for boiling point elevation is going to look like this. It's going to be change in T equals not a negative I, now it's a positive I because we're adding a positive value to the original boiling point. And instead of Kf, you're going to have Kb, which is our boiling point elevation constant. Again, it's a constant that's for whatever liquid whatever liquid is the solvent in your solution. And then it's going to be multiplied by little m, just like the freezing point depression constant was in the last problem. All right, so let's do example 9.8 just to make sure we get this. Like I said, the concept's exactly the same. You add a substance to the liquid and it raises the boiling point. So we're going to find the change in the temperature, and then we can add that to the initial boiling point, and it's going to give us what the new boiling point would be. And by the way, cooks use this because if you add salt to let's say you're boiling, you're cooking pasta in the restaurant and you want it to cook as quickly as possible. Well, if you have a pot of boiling water that you've added salt to before you put the pasta in, you've raised the temperature of that water, right? It's not 100 degrees Celsius, it's hotter than that now. And so because it's hotter, it will actually cook the noodles faster. So when you're trying to do it in a hurry, this is a little trick that cooks use, that it will increase the boiling point temperature of that water. So this particular problem says, what is the boiling point of a solution that is made by mixing 25 grams of NaCl. So we've got 25 grams of salt with 250 grams of water. Now I'm gonna go ahead and write this down as 0.250 kilograms because we know that's what we're gonna need our the mass of our solvent in, because that's what the molality equation requires. And they also tell us, again, they will always give you this constant value. The Kb for water the boiling point elevation constant for water is 0.512 degrees Celsius over molality, okay? So very similar problem, right? We're going to work this the same way, except this time we need to convert 25 grams of NaCl to moles because we're going to need that to be able to calculate the molality. So going to the periodic table, we see that NaCl has a molar mass of 58.44. Oops, put my point too soon, 58.44 grams per mole. And so that means that 25 grams of NaCl is going to be multiplied times 1 mole divided by 58.44 grams. And that's going to give us 0.428 moles of NaCl. And we've already calculated the kilograms of our water, so now let's go ahead and calculate what molality would be. Molality is the moles of the solute, which we just calculated to be 0.428, divided by the kilograms of the solvent, which we have already calculated, 2.25 kilograms. And we do the math for that, and we get 1.71 as our molality, right? And then we're just going to plug that in. Now, how many ions do we have this time? Like we saw previously, NaCl, there are only 2 ions there. You know, if you had something like MgF2, right, there would be 3. Because again, you have a little 1 here and you have a 2 here, so 1 plus 2 is 3. As long as it's an ionic compound, you just add those up, right? So let's plug in 3 for I. We're going to plug in 0.512 degrees Celsius M for Kb. And then finally, the molality we calculated to be 1.71. And we do the math with that, and we get 1.75 degrees Celsius. Now, what is that? The problem asks for the boiling point of the solution. So what's the new boiling point for the water? Well, it's going to be the original boiling point, which was 100 degrees Celsius, plus this 1.75 degrees Celsius, because that's the change in our temperature. So it's going to be 101.75 degrees Celsius. There you go. Hopefully, let me write this up here because I know my head's going to go down there once this video is complete, and I'm not sure how much space it's going to take up. So 101.75 degrees Celsius is our new value for the boiling point of the water. All right. Well, that's it for this chapter. All about solutions, right? You learned some new concentration units, molarity and molality. Like I said, it's important that you remember those formulas. You do need to have those memorized for quizzes and tests. And especially molarity, molarity is going to come back in the future. So make sure you hold on to that information and don't dump it after this chapter. All right. See you later.